Hey everybody, this is Urban, Director of the Ground Truth Track at BSides Las Vegas. The next talk is AI in a Minefield, Learning from Poisoned Data by Itsik Mantin. Itsik Mantin is the head of innovation at Imperva. His work over the last 20 years includes research in web application security, advanced persistent threats, DRM systems, automotive systems, and data security. As a security veteran, he continuously asks, what can go wrong? Just a reminder, the live Q&A will immediately follow the talk, and you can submit your questions via the Ground Truth Discord channel. So I hope you all enjoy the talk. Thanks very much for coming.
Thank you for joining me in the session AI in a Minefield, Learning from Poison Data. I'm Itsik Mantin, lead scientist at Imperva. In the last 21 years, I've been innovating on security, algorithms, and their intersection. Therefore, also my interest in building machine learning technology for cybersecurity and for analyzing threats on AI solutions. I enjoy the game of analyzing threats and designing mitigation. I love problem solving, data science, and in general the art of algorithms. I love building innovative security technology. In my spare time, I love hiking, mountain biking, trail running, and traveling the world and doing everything that you can do outdoors. I'm just finishing now 7 amazing years at Imperva and on my way to the next endeavors. So if you're interested in consultancy on data science, cybersecurity, confidential computing, cryptography, then you can reach out at algorithmsforcyber@gmail.com. I will start with a short introduction about AI and AI threat landscape. I will then zoom into the threat of data poisoning, when, why, and how this threat is effective, and what can we do about it. I will then discuss the problem of learning from web traffic and how the threat of data poisoning is effective there, and again, what can we do about it. And then I will go into the details of a robust learning solution that works in a streaming-friendly fashion without significant memory consumption, and I will end with a summary and conclusions. We are no doubt in the AI era. AI is everywhere. Is affecting almost every domain of our life. AI era is also the data era because data is the material from which AI solutions are made of. But both AI era and the data era are amazing. I love using huge amounts of data in order to build, to create insights that we didn't know before. But AI comes with several caveats with it, and in many cases we tend to ignore these caveats or at least underestimate these caveats, but we'll speak about them today. I think every discussion about AI need to at least mention two significant mega risks or threats that AI brings with it, except for attackers using AI for their purposes. There is the deep fake threat, the ability of actors, usually malicious actors, to synthesize and create images, video, and audio that looks very authentic. We are only see now I think the tip of the iceberg of using this technology for malicious social intents. So this is one threat that's worth mentioning. Another risk there is the AI discrimination, or more accurately, discrimination in the name of AI or under AI, or perpetuation of biases. AI is based on looking at data coming from the past in order to make predictions related to the future. So it assumes that the future will look like the past. And whenever, so it has strong potential to perpetuate biases. And whenever AI technology is being used in order to analyze the credit of someone, for example, if it is a prisoner and what are the chances for a rehabilitation, or whether it is a loaner, what is the chances of him to return the loan, which of course has an impact on the interest he will get, or what are the probabilities of anyone to succeed, then AI has a malicious, a cruel tendency to focus on features we don't want it to feature, or are not legitimate to focus in our modern societies, like gender, race, or color. So whenever you use AI technology for the sake of decision making regarding people, then you should be aware of AI discrimination risk and mitigate it somehow. But today we speak about AI threats, AI as an attack surface. So what you see here is a typical machine learning system. There is training data. It is fed into training, and then it is being used in order to build a model. This model can be a classification model or regression model. And once this model is ready, then it is being used on input data in order to make decisions, to make predictions. In some cases, these predictions are being later evaluated in order to continue and improve the accuracy of the model. When you look at this setup from an attacker perspective, then if the attacker is an internal or if he's an external that somehow found his way in, then of course the sky's the limit. He can do whatever he likes. He can tamper with the model, he can steal the model, he can extract data from the model, he can tamper with data, tamper with the decisions, he can do whatever he likes. However, even if the attacker is an external, then still there is plenty of things he can do. For the training part, he can do what is called data poisoning. We'll talk in detail about this threat later on. To make the model different or to more appropriate for the attacker objectives than to the model owner objectives. And there is also what's sometimes called evasion or adversarial examples or AI deception, which is when the attacker coming to a working model, to a model that is ready, and he creates some malicious data samples that make the model make incorrect decisions. Many of you probably have seen this stop sign that when you add several stickers to it, then that look naive for us, but still for the image classification, for the scene analysis AI engine that lies in the autonomous vehicle, then this stop sign does not look any longer as the stop sign. It looks like a speed limit sign, which of course may have devastating consequences if now this vehicle is coming into a junction. And there is also training data leakage. It is slightly more esoteric threat, but it is still there. When you build a model from the training data, then some of this training data leaks into the model. And in some circumstances, this data can be later extracted by attackers. So whenever you are using training data that is sensitive, it can be PII, it can be health records, or anything like that, you should be aware of this possibility and take adequate actions to make sure it is mitigated. I will start with very a simple example in order to explain the idea of data poisoning. So in the spirit of the Olympic Games that are starting in these days, so we have a gym exercise by the great Simon Biles, and suppose that for the sake of simplicity that the score of this exercise is being calculated by several referees, 6 referees, and suppose it is simple average. Now the 5 referees give pretty high scores because they love the exercise. However, there is a malicious referee, and he wants to make the average 7. Then he will give a -2 score. Or if he wants to make it a 10, he will give a 14 score. Now, this example is very simple, so you immediately can understand what is the reason that this is possible, because the impact of a single data point, in this case the data point that is provided by the malicious referee, is unlimited. He can, if he would have want to have 100 average, he would give it a number that will imply an average of 100. And you can also immediately think about what is the mitigation. First, -2 is not a legitimate score, so you can say that every data point should be valid between 6 and 10, for example. You can, which I believe is actually being done in actual competition. And also you can, this is something that again, as far as I know, is being done in these competitions. You can eliminate the extremes, eliminate the maximal score and the minimal score, and take the average of the others. So this is again, so this is fairly simple to mitigate in this case. I will give a spoiler that things like using the median, for example, is more complicated when you are well, it is easy when you have all the data in your hand in some sort of a batch processing or offline processing, but it's more complicated when you are seeing the data points one at a time and you don't want to buffer them all. Now, I only heard about this terminology of data poisoning a couple of years ago, but this is not a new threat. I mean, I think this is also almost as old as the internet, because probably like myself, when you are looking at TripAdvisor or IMDb or Amazon shopping and you see a rating, then you ask yourself, oh, okay, is this rating authentic? Or maybe this is someone with interest to make this rating high, maybe the owner of this restaurant, or making this rating low because this is a competitor of this hotel. And again, whenever you're building a mechanism that makes a prediction or makes an analysis or uses a logic that is based on data that is coming from users, then the data poisoning threat is there. And indeed, at least in Booking.com, I think they only accept a rating from people from users that actually completed the transactions, actually paid money. So they make it very hard for someone to feed their engine with hundreds of fake reviews. Well, so. And I'm also sure that in other sites you need to be usually you need to be a registered user in order to provide a rating, and moreover, if you now as a user will send 1,000 rating requests in 1 minute, then probably not all of them will be counted as you expect. So how does data poisoning work beyond this example of an average, which is very straightforward? So on the left side, you can see a linear classifier. This line comes to provide the best optimal separation possible between the red triangles and the blue circles, and it does a pretty good job. However, if you only modify the location of a single data point, you can see now that the classifier, it is still a good classifier, it is good, but you can see that it is very different. So there is potentially a significant impact of even one or a small number of data points on the actual classifier. On the right side, you see, again, similar problem. You want to separate the red from the blue. But this time there is an adversary, and he analyzes the situation, and he wants actually to foil this classifier. So he wants to create points in a place that will make the classifier the worst possible. So he identifies this gradient, and he will put these his new data points, data poisoning data points in this location. And what you see now is that you have a classifier that is pretty lousy. Does pretty lousy job now doing the separation. This is exactly what the attacker in this case wanted to achieve. And again, so these are very straightforward data poisoning examples. One of the first battlefields for data poisoning is the area of spam filtering. This is not surprising, because if you think about that, I think spam filtering domain was one of the first where security applications, where machine learning proves itself as an effective mechanism, effective technology. In this case, what you see is an attack on the Gmail. It's an actual attack in 2018 on a Gmail spam filter. What the attackers wanted to achieve, they probably planned to have a spam campaign. They didn't want Google spam filter to identify these spams, their spam, so In advance, they created a large batch of messages. All of them had many things in common with the TBD, with the to be sent spam emails, and they sent them and they they labeled all of them as benign, and they were hoping that what they did will make the spam filtering engine of Gmail to classify these sort of emails as benign, and therefore to create sort of a backdoor within the model. So you can see that all these skewing attempts, which were expressed with a large amount of messages that were classified as this burst of messages detected as spam by the spam filtering. This was this attempt were discovered by Google researchers. Another example, which is slightly different, is sort of an availability attack. This case, the victim is a spam-based spam filter, which is an open source spam filter based on tokens, on building a dictionary of tokens that are correlated with spam messages. But what the attackers try to do here is not backdoors, but to do the other way around. They wanted to pollute the spam dictionary with good words. And this is, by the way, not attackers, these are researchers. But the researchers were able to show that even with control over only 1% of the data used for the training, they were able to make the model classify 80% of the good messages as spam, and in a three-class spam detection, where you have a spam, benign, and unsure, they were able to make the model detect 95% of the benign emails as spam or unsure. Both results render this spam detection model completely unusable. So probably like myself at the beginning, you looked at this example and then you say, okay, we gave the attacker the possibility to provide the data and also to do the labeling. This is a significant power. We gave him to do the labeling. If we wouldn't have given him the power to label, then the problem was not here, right? Wrong, because another variant of this attack works also when the attacker does not have any control over the labeling process. So assume here that the owner of this image classification has some employees that are trusted the labelers. And now the attacker wants to convince, to make the model, to make the training, create a model that will identify all these images at the top of fish to classify them as dogs. So what the attacker does, he takes this image of a dog on the left side, and now he adds to this image invisible noise that is somehow correlated. It reflects the structure or different properties of the images of fish off the top. For us, we still see an image of a dog. And similarly to us, the trusted labeler, he looks at this image and he says, okay, I see here a dog. He labels it as a dog. It is being fed into the training as a dog, an image of a dog. However, when the correlation of this image with these images of a fish makes now the model identify all these images of fish also as dogs, which is again exactly what the attacker wanted to achieve, and it works in both ways. In the top you see images of fish classified as dogs, and at the bottom images of dogs classified as fish. The results are pretty impressive. You can see in this diagram that the clean model classified all these images of fish with very, very low confidence as dogs, and after the attack, then the classification success, the confidence was very high, 95% and more. And again, the most important thing here is that the attacker has zero intervention in the labeling process. So we talked about the threat. Let's talk a little about the mitigation. So there are two prevention mechanism approaches which are pretty straightforward. The first one is to filter suspicious data. For example, if the data comes from suspicious origins like IP addresses or users that we know that we have some reason to suspect them, or in some cases data points coming from bots and not from human users, they can be filtered out. If you think of, again, of booking, then data coming from non-authenticated users can be, cannot provide ratings. Another approach is a fault-tolerant data sampling to limit the impact, which can be the number of data points or the weights, the influence of these data points coming from a single entity. What is exactly an entity? That depends, of course, on the problem, the domains, on the data, on the nature of the data, and things like that. It can be entity, can be a user, it can be IP address. We'll give other examples later on. Other mitigation approaches, which are detection approaches, which by nature is less effective, is to look for significant difference from previous model. When you have several, when the model is evolving, then every time you have a new model, you can compare this model to the previous one. If you see significant difference, then you can you can conclude that you are under data poisoning attack. You can, in some cases, use some kind of a golden data set that every time you have a model, you test it over the data set to make sure that you are it provides the expected results. However, in many cases, you build machine learning models that need to adjust to the reality, and the reality is dynamic and changing. In these cases, these detection mechanisms are less effective. And of course, there is security by obscurity. You can assume that the attackers don't know exactly what you're doing. They don't know what are the machine learning problem you solve. They don't know what is the algorithm that you're using. And therefore, you put your hand in the sand and you can say, okay, they will not be able to attack me. However, we are in BSides. We know that security by obscurity rarely proves itself as an effective security mechanism against actually nothing. Another area which I think worth mentioning, when there is now a new domain of confidential computation, when entities execute logic on data without knowing the data. There are several approaches. Some based on cryptography, like fully homomorphic encryption and functional encryption and MPC. Some based on trusted execution environment and secure enclaves. Some on advanced data science technology like federated learning. The data poisoning threat is still there. There is no guarantee for protection against data poisoning there. And even moreover, any mitigation that is based on processing or validation of the inputs becomes significantly more complicated. If you go back to this example of Simon Biles, then just think that now the training, the entity that does the training now does not see the 9 and the 9.2 and the 14. It does run some obfuscated logic that runs on obfuscated versions of these data points. So it becomes significantly harder to identify that these inputs are invalid. So let me summarize what we have so far. So data poisoning is a significant threat on learning mechanism. It is critical when using data from untrusted sources with or without trusted labeling. And there is no silver bullet mitigation, but there are several mitigation approaches that can at least reduce the risk or throttle attackers, make the attackers work less effectively. And whenever you are using data from untrusted sources and your model is doing something that is meaningful for someone and someone has an interest in making the model make different decisions, and I hope for you that everything that you're doing is making decisions that are meaningful for someone. And this is the case whenever you have a rating system, whenever you're using machine learning for any security solution, a firewall, spam filters, malware detection. All of these are situations where the data poisoning threat is real, is significant, and it will be there. It will be implemented, it will be realized, and you need to take steps again in order to mitigate it. Next, I will move to the area of web security. So most of you are probably familiar with web application firewalls and how they work, but for those that not, I will explain that a WAF resides between an application or API and the outsider world, the outsider threats, aka the internet. WAFs usually are based on a combination of two models, a negative security model and positive security model. The negative security model is based on the assumption that everything is good except for things that we know for sure that they are bad. Sometimes it's called rule-based or signature-based. It has its pros and cons. I will not get into the details of that. The other family of web protection mechanisms are a positive security model, where we assume that everything is bad except for what we know for sure is good, for what we learn that is good. So this is sort of anomaly detection. And in order to get that, we need to learn a baseline profile for the web or API traffic, and to block or alert whenever we identify deviation from this profile. But when I say to learn a baseline profile of web traffic, traffic comes from outside. Outside, it means that we have everything we need for data poisoning. We have data coming from outside, from untrusted sources, and we make decisions that are meaningful for someone. So data poisoning is there. So how does a web or API traffic profile look like? So this is a very sort of a sketch of how such profile can look like. In the center you have these objects marked in red, which sort of think of them as parameters. Can be query string parameters, can be body parameters, can be cookies, which you can think of them as sort of parameters. Each of them is associated with containers, which can be host, URL, method, or a combination of these. And each of them has a traffic profile for this parameter. Traffic profile is likely to include a collection of features, of attributes that are somehow related to web attacks, like the type of the parameter, the multiplicity, whether it can come once or several times within a single request, whether the parameter is optional or mandatory. If it is a numeric parameter, then what are the range of this parameter, of the values? If it is a string parameter, then what is the range for the length of the string, or what are the character sets that is permissible for this for the values in this parameter, and stuff like that. So having that again, a flow that makes sense, at least for me, for using such profile, then first use mitigation 1, which was this filtering, cleaning, to filter suspicious traffic data points that for some reason there is a reason to think they are suspicious or malicious. It can be coming from suspicious IPs or events that were identified as suspicious by any other different rules. It can make sense also whenever you have an attack to assume that to throw away all the data coming during this attack, even if this data looks benign, looks legitimate. And in some cases, it makes sense also to filter out all the traffic coming from automated clients. Next, doing the learning, doing a threshold learning, mitigation 2 to limit the impact of every particular entity. And again, what is exactly the entity? You can use several notions, you can use several of them together. For example, in order to limit the impact of a single IP, you can say that we learn things only if we've seen them from more than X1 unique IP addresses, or more than X2 user agents, or more than X3 geolocations, etc. If you want to eliminate, to reduce, or to limit the impact of a particular hour, because you don't want to learn something that happened many times within a single hour, because this is how good characteristics for attacks. Then you can also look at the hour or day as an entity. And then you have this threshold learning, and eventually you will build a profile, and you have in the enforcement you alert whenever you see deviations from this profile. Now, when you look at this threshold learning that I described, then well, it is fairly easy when you have batch processing, just probably a single or couple of SQL statements, and there you go, you have all this filtering that you want. However, batch processing is not always possible. You don't usually build a profile based on the traffic you've seen in 5 minutes. Probably a day, maybe a week, maybe a month, and you don't want to buffer all the traffic you've seen in a website along a complete month. And there is a need for implementation of such mechanism that work with low memory, works when you see the data points one after the other, and you don't want to buffer all of them together. In order to present the streaming-friendly algorithm, I will take you to a completely different world, completely different problem of a dog food tastiness challenge. We have 2 dog food brands. We have Tio and Pedigree, and we run sort of off a poll of which one of them is preferable by dogs and their owners. And we are getting the raw results that we have 12 likes for Tio and 6 likes for Pedigree. However, we want to prevent bias. We are concerned about the bias of the data. We are concerned about data poisoning. So we want to take a threshold learning mechanism. So we want to accept that a particular brand is good, is tasty, only if we see testimonies, indications for at least 3 cities and at least 3 dog breeds. And here only Pedigree passes, even though it has half the likes of Tio. And if you look at the data, then you see that Tio has many votes from Pomeranians and many votes from New Yorkers, but 0 for San Bernard and 0 for San Francisco, so it has only 2 cities and 2 breeds, while Pedigree have a small number of positive votes from every brand and every city, so it passes the threshold. And the reason for that is that our data was towards Pomeranians and New Yorkers, and they have a very strong tendency to love Tio, which is exactly the phenomenon that we wanted to eliminate its impact. So how it is going to be implemented? So we have Pedigree is an object, tastiness is a fact, a Boolean fact, a binary Boolean facts about this object, and there is 2 attributes that we are looking at. One of the attributes of the votes. One of them is city, the other is breed, and we have threshold of 3 for each one of them. So for each one of them, we need to remember the set of cities and the set of breeds from which we've seen tastiness indications for Pedigree. So we hold the same structure for Tio and the same structure for other facts like the nutritiousness of the dog food brand. And now we have data coming in. And after we see the data, then we have a set of 3 cities and 3 brands for Pedigree. So we pass this threshold test, and tastiness, we have tastiness as part of the profile. However, for Tio, we have only 2 cities and 2 brands and 2 breeds, so we don't pass any of the tests, and tastiness remains not part of the profile. So what we've seen here, that we can learn a Boolean facts, tasty or not tasty, that an object X, in this case dog food brand, has a property Y, in this case tasty or not. Now the memory consumption of our solution is proportional to the number of objects, the number of properties, and the number of attributes, and also to the threshold, because we need to remember the set of cities and brands. However, the more important thing and the most important thing is that it is independent of the size of the data. We don't care if we've seen 1 million votes or 1 billion votes or a zillion votes, still the data structure is not affected by this, by the size of the data, which is exactly what we wanted to achieve in the first place. How to use this for a web or API profile? Well, it is, again, pretty straightforward. During the training, building the profile, every time you see a data point, a request, then you extract that the fact X was seen on this request. Now you collect all these fact X seen together, you check whether they pass all the relevant thresholds, and then you have fact X allowed if you passed all the thresholds, or fact X, or actually exclusive or fact X prohibited if any of the threshold was not met. During the inference, you have a profile, you want to use it. So every request that you're seeing, you extract fact X seen. And now if you have a fact X seen that corresponds to a fact X prohibited, then there you go. You have a violation of the profile. You have something that you've seen and is not part of the profile. And now you can do whatever you would do with alerts. You can block, you can alert, you can do whatever you like. So you are convinced now that we can do Boolean facts, but this looks like pretty limited model. What can you express with Boolean facts? In the next couple of slides, I will try to convince you that you can express pretty many things with Boolean facts. Now, when it comes to the objects, to the existence of parameters and their correlation with combinations of containers, digital locations, hosts, and methods, then this is pretty straightforward because they have a Boolean nature, exist or not exist. So if, for example, you want to express the fact that you've seen a URL X under the host Y, then you have a Boolean fact URL X at host Y allowed. If you want to correlate parameter X to URL Y with method Z, then you have a query string parameter X at URL Y at with method Z is allowed. So these objects and containers and the combination of objects and containers, actually they work pretty well with Boolean facts, no problem here. But what about the traffic profile? We have data types, we have enums, character set, ranges, how we deal with this. So in order to explain that, let's start with the type. Okay. So we have the type can be numeric or string or Boolean or none. It can be also a combination of these because parameter can carry several different types. So for a numeric type, we will use 4 Boolean fact, 4 flags. One of them will be a num type allowed, and it's exclusive or its opposite will be numeric type prohibited. And we will also have non-num type allowed and non-num type prohibited. And it is possible that both num type will be allowed and non-num type will be allowed. It is also possible that both of them, well, it is less likely that both of them will be prohibited. But each one of them has to pass all the threshold tests. We do the same thing for strings. We do the same thing for none, meaning that the parameter contains no value, and for Boolean. And now let's look at a property like type equals strings. Then it is likely that our profile will learn str type allowed, but it will not learn numeric type allowed. So it will learn numeric type prohibited. And it will not learn non-str type allowed. So it will have non-str type prohibited, because all the values that we see all the time are strings. Or maybe we're seeing from time to time something that is not a string, but all these non-strings are not passing all the threshold tests, so they are not part of the profile. And now, whenever we see x equals abc or x@gmail.com, then these are strings, then no problem. If we see x equals 23, then this is a numeric, so it contradicts the numeric type prohibited, and we have violation. If you want to learn that type is a mail address, that the type is, you can only carry strings that correspond, that match a regular expression of a mail address. We are seeing only email address structured values. So str type allowed, and also we have a flag male regular expression allowed. However, non-male regular expression, since we are not seeing non-male regular expression strings, then this flag will be prohibited. So whenever we see x equals abc, which has I'm sorry, which has non-male regular expression, because ABC does not match a male regular expression, we have a contradiction with the non-male regex prohibited flag, and again we have violation. If you want to express the fact that the parameter is mandatory, then we have a flag missing missing prohibited as part of the profile. If now we didn't see that this parameter coming missing, then the missing flag will be prohibited, and whenever we will not see this parameter, then we'll have a violation. If the parameter is optional, then we have the missing flag allowed, and there is no problem when x is missing. When the parameter is not allowed to carry value, then we will have none. I hope that in this point you understand that the left side, the green flags, are not really important, because they are almost meaningless. The more important ones are the red ones. So when we want to express the fact that the parameter shall have no value, then non-type prohibited is the important flag of the profile. When you want to say that multiplicity is prohibited, then multiple occurrences is prohibited. So if you see x equals 3 and x equals 4, then it will have multiple arcs seen, and it contradicts a multiple arcs prohibited. When it comes to a character set, then things become slightly more complicated. You have to do some kind of something that is called the hot encoding in data science world. So you take the set of special characters and you replace it with a collection of flags, each representing a particular special character. So if you want to say that you allow alphanumeric plus colon and semicolon, then you will have ASCII 3A allowed and ASCII 3B allowed, but all the ASCII codes of other special characters are prohibited. When you want to express ranges, then you can use flags. You can divide, you do sort of discretization of the range, and you can use flags that greater than flags and lower than flags, and you get not fully maximum and minimum of the range, but you can get almost very near. You get flags, a profile that is very close to actual ranges. So we've seen how we can learn Boolean facts. So if the profile has Boolean facts, then we're good. But what about other actual machine learning models? So I will speak about how this concept, this approach can be implemented in the area of the class of models that is called decision trees and forest. So a decision tree, essentially, as you can see in the right side, it is a pretty basic machine learning model. For example, you want to know whether an animal is breathing air based on whether an animal is a fish or bird or mammal. These are the classes, and you have two Boolean features, breathe air or lay eggs. Then this decision tree is used to make this decision. And since decision trees are pretty basic models and are usually not sufficient to express the complexity of the problem that you want to solve, then in many cases you use a combination of trees. Some of these combinations are called bagging ensembles, and some are called boosting ensembles. So essentially bagging ensembles are based on taking the data samples you have and build independently a collection of models, and then the result of this super model is the average of all decisions of the models. When it comes to boosting ensembles, then you actually build the model gradually. The model evolves based on the previous model and continues to improve, usually based on samples, data samples that the original model made incorrect decisions. So how can you use this translate these decision trees into Boolean facts? So I'm going to present one way to do that, but definitely this area deserves more research and more analysis. So at the beginning, you build a tree. You build a tree same as before. It can be in batch, in streaming, whatever you like. At this point, you add subleaves to each of the leaves of the tree. You can see here, this is a typical example from sklearn of a plant classification based on 3 features. So you add the subleaf. So for example, on the left side, you can see a leaf where 47 samples of the training data have reached this leaf. It was classified as versicolor. So since there are 47 samples of versicolor, then we have a green subleaf to this leaf. And now we do the same also for the internal nodes. So for example, this guy here, I hope you can see my cursor. This guy here, it has both versicolor and virginica, so we had add 2 subleaves to this one. And now what we do, we use this threshold learning for each of the subleaves, and moreover to each of the paths to these subleaves. So for example, since this subleaf, it has 47 samples, it is very likely that it will pass all the threshold tests and will be part of the validated tree. However, here the green subleaf has 47 samples, which is okay, but the purple subleaf has only a single data point, so probably didn't pass threshold, so it will not be validated. It will not be part of the validated model. And now we actually have a tree. Okay, and this tree is valid. However, we have some odd situations. If we reach this point, for example, we have 2 decisions. If we reach this point, we have no decisions. So and before that we had, we had an exclusive decision. Now sometimes we have exclusive decisions, sometimes multiple decisions, sometimes no decisions. So we have somehow to deal with that, but there are many ways to resolve this. So I'll not get into the details here. So that was for decision trees. What happens when you go to ensembles? So in fact, when you are doing bagging, then it is pretty straightforward, because when we have the models are decision trees, so you do validation of the trees. And now, remember that we have multiple decisions sometimes, and we have no decisions sometimes. Well, this is not a problem, because we anyway do averaging. So during the voting, whenever we have multiple decisions, we can count several votes. Whenever we have no decision, we can count no votes, and it still makes a lot of sense. When it comes to the boosting ensembles, well, you can also use this validation whenever you have a tree, but there is no guarantee that the process will evolve into a good model. So more research is required for boosting ensembles. So let me summarize. Data poisoning is a significant threat on learning mechanisms. Threshold-based learning may provide an adequate, robust learning solution. Again, it has to be exactly tailored to each particular situation and problem and data, but it can provide an adequate solution. The Boolean facts framework provides a streaming-friendly implementation for threshold-based learning, and many features can be expressed with Boolean facts. And eventually, threshold learning of trees and forests is partially possible also with Boolean facts. Thank you very much, and now we have a couple of minutes for Q&A.